Hello everyone. Today we are going to learn about Kadane's algorithm. It's a very famous algorithm. It is also known as maximum sum Subarray algorithm. If I write that down, maximum sum Subarray uh, algorithm. Mm, it is it is very famous and it is very important algorithm, and you can find many blogs and many YouTube videos about the maximum sum survey algorithm. Most of them doesn't cover why the algorithm works. Today my main focus will be how the algorithm works and why always it brings the optimum answer. Okay. Now the algorithm used to solve a problem. And what is the problem? The problem is if we are given an array can be both positive, negative, and zero elements. We take an example here, like -3, 6, -1, 2, 0, and 5. Now we have to tell what is the maximum sum subarray of this array. Maximum sum means the consecutive element which result the highest sum. Okay, if we select first two element, then the sum is 3 minus 3 and plus 6. The sum is 3. Okay, but we can see that it is not optimum. If we take these two in our range, then the sum will be minus, then the sum will be uh, 6 and 2 will be 8, and this will be 4. The sum will be 4. We can see that the sum has increased, but it is not the best. We can have another in this array. If we take the sum of values from 6 to 5, we can say that it is optimum, and we can find any other optimum uh, sum of subarray or maximum sum of subarray in this example. Okay, now we are going to learn how we can bring this. Okay, what can be the brute force approach for this? Mm, the brute force approach or naive approach that we can think about is, let's say it is an array, it is an a start point, and this is an end point. Okay, what we can do is here we can select, we can always select a starting point, assuming that our maximum sum subarray starting point is that. Okay, and ending point, let me erase that starting point here. It will create confusion. Okay, fine. Assume that it is an array. There is no values, but we can assume that it is an array. Okay. The starting point of the array is the starting point of the array, not the starting point of the array. We can assume that we can always choose the all possible starting point and all possible ending point. Okay, we can choose all possible starting point and ending point, we can and we can take the sum of elements in between, and we can run this for multiple start and ending point, and we can select the maximum. Okay. If I submit sum my idea, or in few words, we are gonna choose all possible starting point and all possible ending point of our maximum sum array. We will suppose that ma- this is our answer. Then we calculate the sum. Then we update our sum, the global sum, G sum or answer. Okay, then we are going to choose another ending point, then another ending point, then another ending point. After that, we are going to shift the starting point one cell to the right. Then we are going to, for this starting point, we are going to examine the various type of ending points. And the maximum of all this will be our result. And this is the brute force solution to the problem. Now, what is the complexity of this solution? The complexity will be big O of n cube. Why? We are going to select all possible starting and ending point. If we select all possible starting and ending point, it will going to take roughly or NC2. Okay. This is almost equal to n square, and we are going to take the sum, and we should iterate from first element and last element of our selected subarray to calculate the sum, and this will take another n operation. So total there will be O of n cube operations, and this is a brute force solution to the problem. And if we look at the code of the problem, here it is. This is n cube solution, and here first let me explain everything. N is the total number of values, and we are taking values as input, and Kadane function has been called. We are selecting left position, it means starting position, and for every starting position we are selecting ending positions, which is obviously to the right of the starting position or the left pointer. And for all possible selection, we are calculating the sum of the elements in between, as we have told. So this will take n, this will take and this will take n. So total operation is n cube. Okay, fine. This solution surely works, but we can optimize it. We can surely optimize it little more. And okay, let's optimize it in several steps. Uh, we can actually do better. We we can reduce the n cube complexity to the order of n square. We can do that. Okay, how we can do that? Let's see better solution or better approach n square. Uh, for every for an array, we are choosing every left pointer and every right pointer, and we are calculating sum in between. Selecting every left and every right pointer gives us the computational complexity of n square. Okay, now we are adding all the elements in between. It is giving us more n. And let's see, can we optimize this or we can remove this n. We can do it very easily using prefix sum. Prefix sum. If we take prefix sum of all possible values in the array, prefix sum means let it is an array. And let me give the example by previous ones. Uh, it is our array. So we will create prefix sum. Prefix sum will be sum from its prefix. So we will calculate first minus 3. First will be minus 3. Then minus 3, 6. It will be 3. That then sum will be first 3. So it will be 2. Then it will be 4. Then it will be 4 again. And it will be 9. This is called the prefix sum of the array. Okay. Now what we are doing after selecting first and last index, we are calculating sum in between, which is giving us order of n, only creating the sum or calculating the sum. But with the help of prefix sum, we can do this in O of one time. Just if we want to, uh, let's say, if we want to know only the sum from here to here, so it is not very big deal. All I have to do is take the sum of take the index value of that in the prefix sum, which is 4, and subtract it to the prefix sum of our starting range, uh, not from the starting range, from a position behind from the starting range, which is minus 3. So it gives us the sum of 7. Now let us see minus 6 minus 1, which is 5, and 2, which is 7. So in this way, the sum of a range can be calculated order of in constant complexity, O1 complexity. So this approach is better because we can select n square, and in just O1 complexity, we can select the sum. So if we see the code for this, everything is the same. Uh, Here is the difference. We are taking a prefix sum array. We are creating prefix sums, and it is first two things of the loop is same, taking L and R. And what we are taking is we have deleted the third loop and just taking the subtraction of starting point and ending point, which is giving us the sum of L to R range. So as we have omitted the third loop, this is n square complexity. Okay, it's surely better from the naive approach, but we still can do better. Let's see how we can do better. This is doable in linear complexity. Okay, now this is the tricky part. You have to notice a thing here. Let's assume, let's assume if this is our given array, we will iterate through each position. We will iterate through each positions, and for every position, we are going to take each position as end position of our maximum sum subarray. We will treat each position, we will iterate through each position, and we will treat each position as end position of our maximum sum subarray. And from that, we are going to find the starting position or left position. If it is the end position, left position will be somewhere left to the end position, and we are going to find where it can be, or uh, where we can put that starting position so that we can find we can find the we can find range sum maximum. uh, we are going to find that. Now let's notice in this part. If I if I tell you if I told you that for an array for an array uh, this is the ending position, and this ending position will give the maximum sum. Okay, now your task is to find the uh, starting position. uh, what can you do? What do you do? I have told you that ending position is this, and it is fixed. What you can do is, here you know the this value prefix sum. It is simply the sum from the starting to the end. Now, if you want to find the maximum value, if you want to now your goal is to find maximum value of this function, prefix sum of right and left minus 1, prefix sum of left minus 1. Now if this value is known, then if we want to maximize this subtraction part, it is obvious that we want to minimize the sum of left minus 1, prefix sum of L minus 1. We want to minimize that, which will maximize the total subtraction. Okay, so if I, when I was iterating through from starting to end, if somewhere I already stored the minimum value which I have, minimum prefix sum which I have seen from the start, then I could simply just put the minimum value. Let's say minimum value could be here. So I will just take the minimum value and put it right here, and this will obviously give us the optimum answer for this fixed R, only this fixed R. And it is true. It is true. Because if we want to maximize the subtraction part, we obviously have to minimize the prefix sum of L minus 1, and minimizing the prefix sum of L minus 1 will be give the maximum answer of this subtraction. And it can be said that for no other value, the sum can be maximized. And obviously prefix sum of R of any fixed R left right index will be fixed. So we can use this, and we can easily uh, delete this loop or omit this loop also. Okay. So in a word, uh, we are going to take every right. We will iterate through starting position of the array and ending position of the array, and we will take each value, each index as our right index of our array, right index of our maximum sum subarray. Then we are going to take the already explored minimum prefix sum, and we are going to delete this from the R. And this will obviously give us the maximum sum subarray ended at position R. And this is simply the key observation of Kadane's algorithm, which help us to reduce it to the order of n. And if I explain you the code, everything is same. Prefix sum also is the same, and we have kept a variable name minimum prefix sum. The minimum prefix sum will give us the minimum prefix sum that we already seen when we are iterating from left to right or 1 to n. So we are taking every possible answer ending at I, and we are simply updating the minimum prefix sum from what from which I have explored here. This is calculating the answer of minimum prefix sum. Uh, Sorry, I have made a mistake here. Yes. Okay. This part is giving the maximum answer for which are ending in I, and after calculating that, we should not forget to update what is our minimum prefix sum. So I am updating our minimum prefix sum as well, which will help us to uh, which is help us to find the result for the ending index which are further in the right. Yes. So the computational complexity is order of n, and it is the optimum approach if we tell about the time complexity, it is optimum. But here we can make further optimization. The further optimization is here we have take an extra array mean prefix sum. We can easily delete this or omit this. We can take a simple array which will sorry, we can take a simple variable which will keep track of the maximum prefix sum. Sorry, the prefix sum. Okay, how it can be done without prefix sums? Let's see. Uh, we are going to um, take a sum. I have made a mistake in that code. Here will the sum is equal to 0. Okay. Now what I can do is this sum always indicates the sum from 0th element to the current element. Okay. And this sum is working as prefix sum array. It will always keep the track of the prefix sum or the current sum from 0 to I. Okay. Now everything else is the same. What we are doing here, we are subtracting the current prefix sum. We are subtracting minimum prefix sum from the prefix sum from current prefix sum, and this in our optimized version, the prefix sum is simply the sum here. So we are subtracting minimum prefix sum from the sum, and we are updating the minimum prefix sum as we have also updated here. And by using this, we can easily get rid of the additional memory. It is memory efficient, easily, so much memory efficient. And this also will work in order of n time complexity, but we don't have to use the prefix sum array, extra storage. This is the most optimal version of it, and it is a very famous algorithm, and it is very crucial for coding interview as well. And competitive programming, this is also for competitive programming, it is very important. But uh, there is but straightforward cadence algorithm uh, is we can say rare for competitive programming. Uh, Questions can be somewhat altered or tweaked for this problem. Uh, a question can be asked that what will be the starting position of maximum sum subarray, what will be the ending position of maximum sum subarray, and if there are various type of L and R, uh, you have to give the maximum range of L and R, or if you have to give the minimum range of L and R, where range is the smallest or range is the largest. Range means the difference of R minus L plus 1. It is make it larger or make it smaller, or a different type of variation of it. If you understand the basic algorithm, you can easily come up with this type of optimization. The main goal of this class was There are many lectures, but few of them, uh, few of them only took the the steps to why this algorithm works. And this algorithm, and I have told the brute force approach, naive approach to the optimized approach. So it is very simple to understand why the algorithm works and how the optimization is applied. And if you understand that, this will help you to understand the further uh, the question which are tweaked or which are hard problem from this topic. So yes, that is it. Thank you.